Doctor, you're rolling. You may proceed.
Yes. So we talked about boundary conditions. And boundary conditions, as I said, are clamped end and simple support. I would like to elaborate each of them. So first of all, simple support. Now, simple support means a support in which the beam part, so this is part of the beam, and that is where it is supported. There are two links here. So this type of link. One is a horizontal link, one is a vertical link. And therefore, this beam can rotate. So it can actually take such a position. Okay, it can rotate around this point A. Okay. Now, therefore, okay, first of all, W, of course, equals 0, because this point is restrained. But second, also the bending moment equals 0, because at this point there is a possibility of rotation. So we have two boundary conditions. And this boundary condition, we know from strengths of materials that mz equals EI d2w dx square. So that is modulus of elasticity. And this is moment of inertia. Now, modulus of elasticity and moment of inertia as a product is called a flexural rigidity. And this flexural rigidity is positive. So therefore, when I write mz equals 0, it equals also EI d2w dx square. So I can actually cancel by d. So I get therefore that at simply supported end, we have two conditions. W equals 0 and d2w dx square equals 0. Okay? So these are the conditions that simply supported end. So this comes from the moment. So this is like kinematic condition. This is like force condition or moment condition, but we say that moment and forces are cousins, as we know. Now we go to clamped end. Now, clamped end actually is like this. So this is an end. It is equivalent to two vertical links that are very closely spaced with each other. Two vertical links closely spaced to each other. And the distance, say, imagine between them is epsilon. Epsilon. Now, naturally, W at 0, I mean, say if this is a coordinate system, X. So W at 0 equals 0. So there is a kinematic restriction. And now let us look what happens. What does it mean? But also W at epsilon equals 0. Also. Now, what is W of epsilon? What does it mean, W of epsilon? So we know there is something that is called Taylor series or Taylor expansion. And that is as follows. So W of x at some point, we are expanding at some point. So W of x equals W at A plus dW dx at x equals A, x minus A, plus d2W dx squared at x equals A, x minus A squared, and this is divided by 1 over 2 factorial, plus, if you want, 1 over 3 factorial, d3W dx cubed, x equals A, x minus A cubed, etc. So that is representing W of x in the vicinity of x approximately A. Now, linear approximation means that these terms sometimes are small, so they are negligible. And this one also, negligible. Because x is approximately A. So x minus A is small, of course. But x minus A is very small. Yes, sir? Can you say again? Here? Representing W of x in the vicinity of x approximately A. Vicinity. Or in neighborhood. Or around. Okay? So x minus A is small, but x minus A is already very small. X minus A squared. X minus A cubed is very, very small. Etc. So, therefore, we can actually make this approximation. So, which is like this. So W around, so A is 0. So let us take A is 0 because we want what happens in the beginning. So W of x equals W at 0 plus dW dx, x equals 0, x, yes, x minus A, but this A is 0. But this guy is 0, do you remember? Because at A we have this link. We have two links. So this here, this is 0. So there is a displacement is 0. So what we have is W at epsilon. W of epsilon is approximately W at 0, which is 0, plus dW dx at x equals 0 times epsilon. So in order, this must be 0. Must be 0. Why? Because W at epsilon is 0. There is a second link. Second link. Now, in order this to take place, in order this to be possible, we need dw dx at x equals 0 to be 0. Otherwise, this will not be possible. So therefore, at x equals 0, we have. So we had w of 0 equals 0, w of epsilon equals 0. But so I'm crossing this. We don't use this. W at 0 equals 0, w of epsilon equals 0. We use w at 0 equals 0, and in this case, dw dx at x equals 0 equals 0. So we have these two conditions. Function is 0, and first derivative equals 0. So it's a lengthy derivation. A bit. It should be given in strengths of materials, but people either don't know or don't give. And now what happens is that, so if this is a beam that is clamped, say clamped free, then displacement is like this. Okay? So this is a displacement. So that here w is 0 and w prime is 0. Okay, first derivative is also 0. That is a deflection shape. Okay, deflection shape. If I have two, on both sides clamped, say like this, and then deflection is like this. And maybe I use different color. Okay. So here w equals 0, w prime equals 0, w equals 0, w prime equals 0. Okay. So I dealt only with two boundary conditions up to now. We will deal with other boundary conditions later on. Then what we did was we had this functions, k functions, if you remember. And before proceeding further, I would like to ask you that you write down these functions on a separate page. So please write down these functions on a separate page and put this transparency or a special sheet next to you, so that every time these functions will be next to us. Please tear a page from your notebook and write down these functions separately. So you will have them inside, but we will also have them outside, so to say. You have to tear the page, because I would like you to physically have it separately. So please write down these four magnificent functions, Krylov functions. And this page should remain in front of you all the time, I mean, during this lecture at least, and a couple of others, several others. If you want to remember these functions, you can remember like this. First function is sum of cosine. Okay, first of all, hyperbolic cosine and cosine. That is the first function. Third function is difference of them. Third. Hyperbolic cosine plus cosine. Third function is hyperbolic cosine minus sine. Now, second function is sum of hyperbolic sine with regular sine. Fourth function is a difference of these two. Okay? So first and third are easily to correlate, plus minus. Now, second and fourth are also easily correlated, plus minus, if you want to remember. But as someone said, it is better to have a sheet of paper with you and don't have to remember the functions. Okay, now we have beam which is simply supported at its ends. Beam is simply supported at its both ends. Now conditions. The length of the beam is L. So you may want to write length of the beam is L. Length of the beam. Now, what are the boundary conditions? Boundary conditions are absolutely the same because left side is simply supported, right side is simply supported. So function and second derivative equals 0. Function and second derivative equals 0. Now I write the solution, W of x. W of x equals A1k1 plus A2k2 plus A3k3 plus A4k4 of alpha x. Now please write down W at 0 equals 0 here. W of 0 equals 0. That means A1 K1 of 0 plus A2 K2 of 0 plus A3 K3 of 0 plus A4 K4 at 0 must be 0 here. But K2 at 0 equals 0, K3 at 0 equals 0, K4 at 0 equals 0. So they are falling down, so to say, automatically when I substitute 0. And K1 at 0 equals 1. So therefore, from that condition, I get A1 is 0. A1 must be 0. Otherwise, W at 0 will not be equal 0. It's very nice, is it not? I mean, because we have this interesting set of functions, you may want to write this. Because we have this interesting set of functions, A1 equals 0 immediately. We find that A1 equals 0 immediately. It's very important to note. Now this Mr. Krylov was very, very clever guy. He says, when I differentiate, okay, when I differentiate this guy 2 times, okay, when I differentiate 1 time, I get K0, which is K4. K4 at 0 equals 0, so this guy will be not participating. Derivative of this is K1, and then derivative is K0, which is K4 at 0 equals 0. Not there. Derivative of this is K2, and then derivative is K1. K1 at 0 equals 1. So therefore, I will get only A3, and this guy's second derivative is K2. So therefore, A3 must be 0. You better write this. I will wait a few minutes so that you will be able to write this by your words, in your words. So these are magnificent functions. They make our life easy. They are exciting functions. Because these K's have very interesting properties. Had I been dealing with sine, cosines, and just then that would not be the case, and I would have huge equations. So if A1 and A3 are 0, then I'm left only with 2 coefficients, A2 and A4. So A2 and A4. So A2, K2 plus A4, K4. So these are left. Now I have to satisfy boundary conditions at L, x equals L. I get A2, K2 alpha L plus A4, K4 alpha L equals 0. Then second derivative of this. Okay, first derivative will be K1, second derivative will be K0, which equals K4. A2, K4 alpha L plus first derivative is K3, second derivative is K2, K2 alpha L. Okay, so I got 2 equations with 2 unknowns. A2 and A4. Now, this is an algebraic system of equations which is homogeneous. Homogeneous means here I have zeros. I have zeros on the right-hand side. And now, let me just remind you one thing here. When I have a system of 2 equations, say, with 2 unknowns, let us say, 2x plus 4y equals 19, and 7x plus 9y equals 35, say. I just wrote some randomly these numbers. So we know how to find x. X equals determinant. Okay, here is the determinant, 2, 4, 7, 9. In the numerator, I write 4, 9, the same here, but instead of the first column, I should write column of these 3 terms. And how much is y? Y equals, denominator is the same, 2, 4, 7, 9. Numerator is 2, 7, 19, 35. Okay, we know that. Unique solution if determinant which in numerator is not 0. Yeah? 2, 4, 7, 9 must be not 0. And indeed it is not 0. 2 times 9 minus 4 times 7, it is 18, minus 28. It is minus 10, and if you remember, minus 10 is not 0. Okay, now, if I have a homogeneous, because that was a non-homogeneous. Non-homogeneous set. So non-homogeneous set then has solutions that is calculated by this equation. Now what happens for homogeneous set? Okay, so let us write 2x plus 4y equals 0. 7x plus 9y equals 0. Oh, it's very easy. We know the determinant is not 0. So x equals 2, 4, 7, 9. So that is 4, 9. Here now, free coefficients are 0 and 0. So then this is 0 divided by minus 10, which is 0. Y equals 2, 7, 0, 0, and then 2, 4, 7, 9. So this equals 0 because 2 times 0 minus 0 divided by minus 10 equals 0. So what we have is as follows. If a homogeneous set has a non-zero determinant, then solution equals, or solutions equal 0. If the determinant is non-zero, like in this case minus 10, then solution is 0. Okay? If it is a homogeneous set. Okay? We knew that, of course, from childhood enough. We studied this in kindergarten. Okay, now let us come back to our problem. We come back to our problem. Here, if determinant I wrote is not 0, then A2 and A4 are 0. So that is very simple. That is what I brought you an example. If determinant is not 0, then A2 and A4 are 0. Now here you have to write down here. But we do not want A2 and A4 both to be 0. We do not want this. Why? Because, please write down here, we do not want A2 and A4 both to vanish. Here you write. We do not want A2 and A4 to both vanish. Because then W will be totally 0. because W is A2 times K2 plus A4 times K4. So then it will be 0 times this plus 0 times this, so that will be 0. Then W will be, then there will be no vibration. There would be no vibration. There would be no vibration if A2 and A4 were 0 both. There would be no vibration. But we are discussing the vibration. The whole course is called vibration. We want vibration. So therefore, determinant must be 0. So therefore, now 4 we say A2 square plus A4 square not 0 means A2 is not 0 and A4 is not 0 simultaneously. Determinant should vanish. I think it's easy. So then determinant of what? Determinant of coefficients in front of A2 and A4. So that is K2, K4, K4, K2. It's a nice determinant. K2, K4 in the first row and K4, K2 in the second row. So then determinant equals K2 square alpha L minus K4 square alpha L equals 0. That is this determinant, because this times this minus this times this. Yes. So now we have to write down what is this K2 and K4 and substitute here. You have this on the list. K2 is hyperbolic sine alpha L plus sine alpha L. This taken half and squared. Minus 1/2 hyperbolic sine square minus sine alpha L squared. And so I can calculate if you want. So look, please. Hyperbolic sine alpha L I can denote by capital S. Hyperbolic sine simple sine alpha L I can denote by small s. So I have here, first of all, 1/4 s square plus small s square plus 2 capital S small s. Then minus 1/4 s square plus small s square minus 2s small s. Look, now this term, these two terms and these two terms are vanishing together. So this is 2 over 4 is 1/2, and then there is also 1/2, so that will be just small s times capital S. So then this equals, look please, hyperbolic sine alpha L times sine alpha L equals 0. I just substituted it back. Hyperbolic sine of alpha L never equals 0. So therefore only sine alpha L can equal 0. Sine alpha L. Now sine alpha L equals 0 under several cases. First of all, alpha L equals k times pi. In order sine to be equal 0, argument should be proportional to pi. This k equals 1, 2, 3, 4, etc., 1,000. So paying attention, we found infinite amount of solutions. You may want to write it down. This is unbelievable. I was looking for just one solution. We were looking for just one solution. We found infinite number of solutions. K equals 1, 2, 3, 4,000, 2,000, 5,000, million, 2 billion, 1 trillion, etc. 800 billion, numbers that we hear very often recently. So please write down. This beam has infinite amount of natural frequencies. So now this beam actually justifies to have also 1 degree of freedom systems that we studied for 1 month. Why? Because now we just have infinite amount of 1 degree of freedom systems. Please write it down. Beam represents in itself infinite amount of 1 degree of freedom systems. If you want to speak gastronomically, like 1 degree of freedom system is a person who eats his lunch, dinner, breakfast always alone, without interacting with other people. Okay? Beam indifferent. Beam is inviting every time. He's inviting infinite amount of people to his home. So you may want to write down. It's very different systems. He's very outgoing. Beam is very outgoing person. 1 degree of freedom system is a loner. Beam is very sociable. I don't want to say which one is bad. I mean, I don't want to say this is better, this is not. He just has infinite amount of people. He cannot eat alone. Okay, now the question is how much are the frequencies? Okay, where are these frequencies? Okay, frequencies are here. If you remember, we had this notation, alpha in force power. That was our notation from past lecture. Rho A omega square over EI equals alpha in force power. That is how we denote it. We divide the differential equation, if you remember, by EI. In the second place, we had rho A. Then it multiplied by omega square because derivative by time gave omega square. And then we said, okay, we will denote it by alpha in force power. So from here, omega square equals EI alpha in force power divided by rho A. But alpha in force power from here, please, equals K pi over L. K pi over L in force power. So because there is K equals 1, 2, 3, etc., whatever you want. Any positive number. So this case frequency can be denoted as omega k. This is case frequency. If you have any questions, please do not allow me to continue without asking me a question. So omega sub k equals then square root from this. Square root of EI over rho A times k pi over L squared. Any questions? Any comments? Yes, sir.
So if it has infinite number of natural frequencies, why doesn't the beam just kind of take itself apart?
Oh, okay. Student is asking, this beam has infinite amount of natural frequencies. Why does not it shake itself apart? My answer to this question actually is given by the question. Why should it? I mean, there are many frequencies there, but when you have, say, a big party with many guests, this company does not shake it itself apart because they are well-behaved guests. Is it right? Say recently, there was a very big party in Washington, D.C., and everything went very nicely, very fine. So the same happens here. All these natural frequencies, I mean, beam has combination of natural frequencies. I mean, it has infinite amount of frequencies. But these frequencies, some of them are small, some of them are big. So for example, when you have guests, some are eating big amount of pizza, some others are small amount of pizza. Everything is okay. We will see later that everything is in order. Sometimes things are not in order naturally. It could happen when excitation is very specific. Suddenly we knew there is a resonance phenomenon, etc. Now there is more possibilities for resonance. If outside frequency, excitation, coincides not just with one frequency, but any of these frequencies, suddenly response may go to infinity. Yes, it is more dangerous from that point of view. On the other hand, we will see that response does not have to go to infinity. There is no reason for that. Just it is a combination of many one degree of freedom systems, which is very nice result. If it is not satisfactory, please continue. Let us continue the discussion. I like discussions. Any other questions? Please, from the first row, second row. Yes?
I guess the response is only one. Why should we get a measure?
Yeah, okay, the question is about response. Let us answer this very in short. We did not deal with response. So it will depend on excitation. So we will see, wait and see. Any other questions? Yes?
If it has infinite number of natural frequencies, if those frequencies combine? And if they do combine, wouldn't that remove some, and then you have more of another? If you have the...
Yes, the question is whether these frequencies combine. Pay attention. I personally do not know what does it mean the frequencies combine. Because say there are different frequencies, omega 1, omega 2, omega 3, etc. The question, of course, is probably what you are asking me is as follows. How all of these natural frequencies form after that a response of the system? So that is a very interesting question, which is how do I calculate the response of the system which has so many natural frequencies? That is a question that I cannot answer now, but I can answer it very shortly like this. Because this beam is a combination of infinite amount of one degree of freedom systems, then actually my answer will be as follows. Calculate the response of each of the system and then sum them up. You will have infinite amount of summation. we will have at the end summation, infinite summation, k from 1 to infinity. And then things should be summed up. Okay, you may say, okay, that is very tedious task. Yes, this is a tedious task, but thanks God we have His Excellency as a computer. So we can actually program this summation and get the result.
Can you integrate to do a summation?
Yes. The question was whether I can integrate to do the summation. Answer is yes. There is even a method that is called method of integral estimation. That is integral estimation of summations. It was by chance done by my advisor, scientific advisor. Okay. Yes, other questions?
I guess I can see some, I don't know how to express it properly, but I can see a discrete concept in combination with a continuous concept as well.
Which concept? Discrete, yes.
Discrete.
Student is, I mean, the person is correct. Person says that he sees infinity here, infinite amount of frequencies, but he also sees discreteness because these frequencies are separated. They are not, I mean, any frequency. You cannot pick any frequency and say, okay, this is a frequency. Say from 0 to 1, every frequency is a natural frequency. No. There is first frequency, then second frequency. To calculate first frequency, I have to put k equals 1. To calculate second, I should put 2. Then to calculate third, I should put 3. To calculate thousandth frequency, I should put 1,000 here. So they are separated. Okay, additional question, which I like. I would like actually everyone to ask at least one question. Yes.
So is that equation, so omega k is a magnitude?
No. My question is whether omega k is magnitude. No, omega k is not a magnitude. Omega k is a natural frequency. It is a value of the case frequency. The magnitude has to do with the response. We do not deal with the response yet. We don't deal with the response. We deal with natural frequency. What is natural frequency? Natural frequency does not depend upon excitation. It is natural. It only depends upon the beam's characteristic. It depends on modulus of